Hello students, my name is Ravi Ranjan Kumar and I welcome you all to this last session of rotational motion. Okay, this week total we have concluded already 5 lessons and this would be the last one. Okay, so without losing any further time, let's share our screen. Okay, so here we go. In today's lecture, we are going to cover some more problems of accelerated rolling. Okay, and then we will finally look into some problems where we will be having multiple axis rotation. Okay, so we must start with some problems of accelerated rolling, and the famous problem here is rolling down an incline plane. Okay, so let's say we have a inclined plane of angle of inclination theta, and over which we have a round body. Okay, this round body could be anything. It could be solid sphere, hollow sphere, solid cylinder, hollow cylinder, whatever it would be. So let's say this is its center, and let's say its mass m and radius r, and its moment of inertia about an axis passing through its center of mass is mk square. We are very well aware of the physical quantity k square by r square, what is its value for different round bodies. So these are the parameters that has been given to us. So we have released this sphere, okay, from rest. Okay, and we now are interested in, as this sphere or as this round body will roll down the incline, what would be the acceleration of its center of mass, let's say a naught. And we are also interested in finding out the angular acceleration of this body. And in this question, this information is also given to us that this inclined plane is sufficiently rough, okay, for this rolling to happen. Okay, sufficiently rough means like friction will be able to prevent slipping at the point of contact. Over here there would be no relative motion at the point of contact of this round body and inclined plane. So once we are given with all these informations, we are required to find out a naught and alpha. So how are we going to find out this quantity? So this is the problem of dynamics of rolling over here. So now you see, uh, so first equation, we can write the equation of force, and then we can write the equation of torque, and we can solve them to get a naught and alpha. But before doing that, we need to draw the free body diagram of this sphere over here. So the free body diagram, so first of all, it will be having component of its weight down the incline. It would be mg sine theta, and perpendicular to incline it would be mg cos theta, as we know. So this is the component of weight. Apart from that, at the point of contact, this will be experiencing a normal in the direction perpendicular to incline, and at this point over here there would be friction up the incline. So these are the forces acting on this rolling round object in this instant. Okay, so now equation of force, when we will be writing, like two methods we are going to use in order to solve this question. Okay, in method one, I will be using combined translational and rotational motion dynamics. So we will be assuming that this body is undergoing purely translational motion of its center of mass, and it is at the same time it is undergoing purely rotational motion about an axis passing through center of mass. So okay, so method number one, we will be assuming CTRM, combined translational and rotational motion. So we are required to write the equation of force. So equation of force down the incline would be nothing but mg sine theta minus f is equal to m times a naught. So that is our equation number one. And we will be writing the equation of torque about an axis passing through center of mass. Okay, which in this figure it is perpendicular to this plane as well. So now you see about C, mg sine theta, mg cos theta and normal are not producing any torque. Okay, the only force producing torque about point C is the friction, and that would be in anti-clockwise direction. So the torque here is F into R, and that would be equal to I alpha. And I here we will be writing it as mk square, and alpha, this relationship, like since we have been already given that the conditions, the like friction is sufficient enough for pure rolling, so pure rolling condition is alpha is equal to a naught by r. So moment of inertia into alpha, when we are writing, we can simply write a naught by r over here. So now these two equations we are having, in these two equations we have two unknowns. This is friction and this is acceleration. Okay, once we got acceleration, we will be able to get the value of alpha as well. So there is no problem in that. Okay, so I just want to rearrange the second equation in this form. Like that would be k square by r square times ma naught. So this is basically equation number 2. Okay, so using equation 1 and equation 2, we can very well solve for a naught, and we can find out the value of friction as well. So the value of a naught we will be getting is g sine theta divided by 1 plus k square by r square over here. So that will be the value of acceleration, and the value of friction, when we will be substituting the value of a naught in the first equation, we will get the value of friction as well, and that will turn out to be k square by r square upon 1 plus k square by r square into mg sine theta. Okay, so these would be the value of acceleration of its center of mass and the friction uh, in this condition over here. So we have been saying already that the friction is sufficient enough for rolling. That means like this friction over here must be static and must be less than equal to mu n. So the condition for rolling, when we are saying conditions are sufficient for rolling, what is that sufficient condition? So let's say condition of friction for rolling. So the value of friction we have already got. So this friction here must be less than equal to mu n. So the value of friction, as you see, is nothing but k square by r square divided by 1 plus k square by r square into mg sine theta, and that got to be less than mu times, and normal here would be nothing but mg cos theta. So let's just rearrange that expression. So that will give us k square by r square upon 1 plus k square by r square, and that was mg sine theta, sorry. So mg and mg will get cancelled, and it would become tan theta, and that quantity got to be less than equal to mu. So if this condition is met, then only we will be able to say that friction is sufficient for rolling. And if this quantity, like this quantity at left hand side, is greater than mu, so then there would be slipping, okay, and there would be no pure rolling over there. Okay, so this was the condition for pure rolling. Okay, and now let's look at the kinematics of this situation now. So see, this is the incline, and the angle of inclination is theta, and this is the round body, and we have already found out the acceleration of its center of mass, and we have already found out the angular acceleration alpha as well. So let's say uh, it it has to roll down the incline by a length of, let's say, S. Okay, and we are now interested in that, like, how much time will it take for this sphere to roll down the incline, and what would be its final velocity, final angular velocity, etc. Okay, so time to roll down the incline, if we are trying to find out. So the acceleration of center of mass, we have already got a naught is equal to g sine theta upon 1 plus k square by r square. So you can see this is the motion of its center of mass is uniformly accelerated motion. So in that case, time would be nothing but root under 2s by a naught, or you can say root under 2s by a naught is basically g sine theta into 1 plus k square by r square in the numerator. Okay, so this will be the value of the time it will take to roll down the incline by a distance s along the incline. Okay, so this is the time, and similarly we can find out the final velocity. Okay, final velocity of its center of mass, let's say v naught. Okay, so now see here, like its initial velocity was nothing but equal to 0. So v naught down the incline would be nothing but 2 a naught times s, and again we will be substituting the value of a naught, so that would be 2 g sine theta divided by 1 plus k square by r square into s over here. So these are the values. So now see, this quantity 1 plus k square by r square, this quantity 1 plus k square by r square is appearing everywhere in these relationships over here. So like for example, uh, greater the value of k square by r square, okay, less will be its acceleration, less will be its angular acceleration. Okay, and less will be its angular acceleration means, or acceleration, the greater time, like you can see that t is directly proportional to root under 1 plus k square by r square. So greater this value, more time it will take for this body to roll down the incline, and it will be have a smaller linear velocity, or velocity of center of mass, as it reaches to the bottom of incline. Means greater the value of k square by r square, rolling is a little bit difficult for that, we can say. Okay, because it is having greater moment of inertia. So generally a very simple question, like generally let's say there are different kind of round bodies, and the value of k square by r square we can have. Okay, so like for example, we have a ring or hollow cylinder. Let's say draw a table. This is a round body, and this is the value of k square by r square. And we can have a disc or solid cylinder, and we can have solid sphere, and we can have hollow sphere. So we know the moment of inertia of these round bodies about their principal axis. So for ring or hollow cylinder, the value of k square by r square will turn out to be equal to 1. For disk, it will be turning out to be equal to 1 by 2. Solid sphere, it would be 2 by 5, and for hollow sphere it got to be 2 by 3. So once we know the value of k square by r square for different bodies, okay, so let's say this is body number A, this is body number B, body number C, and body number D. So if somebody asks, like, if we roll down all these bodies down the incline, which is going to take the greatest time and which one would be going to take the smallest time, etc., arrange in ascending or descending order, and what would be their final velocities arranged in ascending and descending order. Like for example, if we are to compare the time, so you can say like the value of k square by r square would be greatest, okay, for this ring or hollow cylinder. So you can say ta would be greatest over here. So after that we are having um, this as greatest value, so t by 3, so td would be after that, and after that it would be tb, you see, and after that you will be having tc. So if we are uh, rolling all these bodies down the incline, so this will reach first and this will reach at the last over here. But this we can say only when friction is sufficient enough for rolling. Okay, if the incline is frictionless, in that case there will be no friction, so there will be no torque due to friction. So this is the round body will not be undergoing any rotation, it will be simply undergoing purely translational motion. So acceleration of its center of mass will be simply g sine theta. Okay, so we can say in that case that a time taken by all these bodies, since their acceleration of center of mass down the incline would be g sine theta in all the cases, the time taken by all the bodies will be same over here. So this is one typical problem. One another simple question, or before moving on to any question, let's also study the energetics of this situation. Energetics of rolling down the incline. Now see, so this is the body, okay, and its moment of inertia about center of mass was mk square, and m is its mass and r is the radius. Okay, so let's say it has rolled down the incline by h, and let's say this, or s, let's say s, and this angle is theta over here. So we have already got the value of a naught and we have got the value of alpha. Okay, alpha is basically a naught by r. So final velocity, the final velocity when it reaches over here, the center of mass's velocity v naught will be equal to we have already said that will be equal to root under 2 as. Okay, so 2 and a was nothing but g sine theta divided by 1 plus k square by r square into s. Okay, so this was the final velocity. Okay, so we wish to find out like what would be the final kinetic energy when the ball is here. What would be the final kinetic energy of this body? So we have already understood the relationship of final kinetic energy. Final kinetic energy would be, we have already got the expression, that would be half m v naught square into 1 plus k square by r square. So that is equal to, you can say, half m, and when the value of v naught square we will substitute, so this will be simply 2g sine theta into s divided by 1 plus k square by r square into 1 plus k square by r square term over here, so which will get cancelled, and what we will be left up with only mgs sine theta. So that is the final kinetic energy. Okay, so here the change in kinetic energy, simply we can say change in kinetic energy would be kf minus ki, and initial kinetic energy was nothing but equal to 0, so that is going to be equal to mgs sine theta. mgs sine theta. And similarly we can also find out the change in potential energy. Now you see, so see, the center of mass of this body has come from here to here, so the vertical height descended is nothing but s sine theta over here. This is say h, so the potential energy would be decreasing by mgh, so that would be change in potential energy is minus mg into s sine theta over here. So interesting thing to find out here is work done by friction. Work done by friction. And work done by friction we can find out using principle on rather work energy theorem over here. So work energy theorem simply states that work done by some external force or non-conservative force would be equal to change in potential energy plus change in kinetic energy. So change in potential energy we have got minus mgs sine theta, and change in kinetic energy is plus mgs sine theta. So this is going to be equal to 0. So work done by friction over here is equal to 0. Okay, so that is like what we should have expected, because as we said, friction here was sufficient enough for rolling, so that means there was no slipping at the point of contact. So this is the point of application of friction. So the displacement of the point of application of force is equal to 0. So in the lecture of work done by a force, work energy power lecture, we have already discussed, whenever we are writing work done by a force is equal to force dot displacement, the displacement is of the point of contact, and here, or point of application of force. So here point of application of force is point of contact here, the displacement of which is equal to 0 because it is not slipping. Okay, so we would have expected this result over here. So work done by friction will be equal to 0. So now let's solve one another interesting case. This is the problem of unwinding. Sorry, unwinding tape roll on incline. That is a very interesting problem. Let's say we have an inclined plane of angle of inclination theta, and here say we have a tape roll which is tightly wrapped. Okay, and the length of tape, let's say length of tape is L. Okay, and initially it is here. Okay, and say initially it is at height, or simply it is somewhere on that incline, so we are not giving any height. So what we are interested in finding out, so if it is not slipping, okay, if simply it is unwinding or unrolling, so at this point of contact there is no slipping, if it is given to us, can we find out like how much time will it take to unroll, okay, or unwind over here, how much time will it take to unwind. Okay, and only the information that has been given to us is length of the tape and the angle of inclination, and let's say also it is given that friction is sufficient for rolling, etc. Means rolling is happening. Okay, so how are we going to find out the time? Okay, so the idea here is, okay, this winded tape, we can assume it like its mass distribution is very similar to the mass of a solid cylinder. So its moment of inertia would be nothing but mr square by 2. So the value of k square by r square in this case is going to be equal to 1 by 2. Okay, and as it unrolls over here, you must understand that its mass would be decreasing and its radius of the tape will also be decreasing. Okay, but the thing is, it will still maintain the same kind of mass distribution around the axis passing through center of mass. So the value of k square by r square is not going to change, it will remain half. So that means no matter what is its mass and what is its radius, as it unwinds, its acceleration of its center of mass is still going to be expressed by this relationship g sine theta divided by 1 plus k square by r square, which we have derived earlier. And once we substitute the value of k square by r square in this expression, which is equal to 1 by 2, this will turn out to be 2 by 3 g sine theta. Okay, so this is the idea. Like a naught we have found out, and once a naught we have found out, the another thing to realize is, like, tape unwinds completely when distance traveled by the rolling cylinder is L. Like for example, this is the position, okay, where the this thing has completely unrolled. So the length it has traveled is going to be L only. Okay, so in that case, we have already established the expression for time. So when this is the acceleration and this is the displacement down the incline, the value of t will be given with the help of this formula, root under 2s by a, or a naught over here. And s would be simply L over here, and a naught, as we have already derived, so that will be equal to 2g sine theta by 3. So that is simply uh, 3L by g sine theta. Okay, so this was one interesting problem. So now let's move on to some problems, okay, where we would be having slipping at the point of contact. Okay, means you can say uh, either it can be forward slipping or it can be backward slipping. So let's take one case of forward slipping. Okay, so say this is some rough horizontal surface, and this is some, let's say, for example, let's take this as a solid cylinder. Okay, so moment of inertia about its center of mass would be nothing but mr square by 2, where m is its mass and r is its radius. Okay, so this is resting on the surface, and suddenly we have imparted some initial velocity u to this solid cylinder. Okay, initially its angular velocity was equal to 0. Okay, and this surface is rough, and the coefficient of friction between this solid cylinder and this surface is, let's say, equal to mu. So first of all, we have to understand like what kind of slipping it is. So if it is slipping, so there would be friction at point of contact. Okay, and that friction will be producing some angular acceleration and acceleration, etc. So how are we going to approach this problem? Now you see. So when we will be drawing the free body diagram of this, or before that, let's understand this situation. So this point of contact here, this point of the contact over here, due to translation, it has its velocity in forward direction, same as velocity of its center. Okay, so this has tendency to move forward, so there would be friction which will try to oppose its motion, and that will act in backward direction. So this is F. Okay, and this would be normal, and this would be mg over here. So obviously in this case, normal is equal to mg. Okay, and F will be equal to mu times n. That will be equal to mu times n because the slipping is happening over here. So this friction is kinetic friction over here. So mu times n, that is equal to mu mg. So that is the uh, so that is what we have got, is the magnitude of friction. Now you must realize that initially this cylinder is not rolling, but what will happen, that this friction will produce the linear retardation. So acceleration would be opposite to velocity. So a naught we can find out, and this friction will be producing angular acceleration in this direction. So alpha we could find out over here. So the role of a naught would be to decrease the velocity, decrease the value of u, and the role of alpha would be to increase the value of omega, such that finally v is equal to r omega, which is nothing but the condition of pure rolling. So after some time, this solid cylinder will begin to have pure rolling as its motion. Okay, and we are interested in, let's say, how much time will it take, okay, for the pure rolling to begin. And finally, when the rolling has begun, there would be no friction acting on this rolling body any longer. So at that instant, it will be moving uniformly. So what would be its final velocity, or final angular velocity, or final kinetic energy, etc.? We are interested in finding out all those things. Okay, so before proceeding, we need to understand, like, first thing we need to get about, like, what would be the value of a naught and what would be the value of alpha over here. So the value of a naught we can find out using the equation of force. So obviously the value of a naught, okay, which is in backward direction. So the only force acting in horizontal direction is the friction, and friction is nothing but mu mg, and that divided by mass would be equal to simply mu g. So the acceleration of this cylinder is mu times g in backward direction. Similarly, we can get the angular acceleration. Alpha direction is shown in the diagram. So the friction force here, this friction here would be producing anti-clockwise torque, or sorry, this would be a clockwise torque. So clockwise torque about center of mass over here. So that is nothing but F times R. So that is mu times mg into R, that is the torque, and that divided by moment of inertia of this cylinder about an axis passing through center of mass. So this is going to be mr square by 2 over here. So the value of alpha we have got is nothing but 2 mu g by r. So once we have got these values, so let's say after time t, okay, we can find out what would be its final velocity and what would be its final angular velocity. So v, you understand the formula we would be applying is u plus at. So a is negative in this case, so simply this would be u minus a is mu g, so that would be mu times g times t, and omega would be nothing but alpha t, and alpha is nothing but 2 mu g by r times t. And now using these relationships over here, we can say for pure rolling, this v which we have found out and this omega which we have found out. So let's say after time t, the pure rolling begins. So at time t, v will be equal to r omega. So that will be giving us u minus mu gt is equal to r times omega. So that would be r into 2 mu g by r into t. Okay, so solving this, we will be getting the value of t is equal to u by 3 mu g. So this is the time after which the pure rolling will begin. Okay, so now you see, so at this time, the final velocity we can find out, or final angular velocity. Let's first find out. So the final angular velocity is nothing but this quantity. So once we substitute this value of t, which we will be getting as 2u by 3r, and v will be simply equal to, since v is equal to r omega finally, so this will be equal to 2u by 3 here. So these are the final angular velocity and velocities. One other interesting thing One other interesting thing to find out here is work done by friction in this case. So we should expect that work done by friction this time will not turn out to be equal to zero, because here there is slipping at the point of contact. Okay, and definitely there would be some negative work done by friction. So let's try to find out the work done by friction. Let's use another color pen. So work done by friction in this case. So basically we will be looking at two methods in order to find out that. So let's say, let's again restate this problem. So we have already seen that the acceleration of the center of mass before the rolling happens was equal to uh, a naught was equal to mu g, and there was angular acceleration alpha in this direction, which was equal to 2 mu g by r. So now you see, like, this is the point of contact. Okay, so this was slipping in forward direction. Okay, so what would be the acceleration of this point? What would be the acceleration of this point? So acceleration of this point we have already learned. Okay, uh, that would be due to translation, it would be a naught in this direction. Let's say this is point P. So the acceleration of point P would be due to translation, this would be equal to mu g, and due to rotation, that this would be alpha r, so that is going to be equal to 2 mu g. So collectively what we can say, that the acceleration of point P would be nothing but equal to 3 mu g in backward direction. The acceleration of this point P is 3 mu g in backward direction. So now the thing is, as the initial velocity of this point was equal to uh, what we can say over here, so acceleration we have got, so the displacement of this point here we will be able to find out. So what will be the displacement of this point? So simply we can say that sp, displacement of this point in backward direction, is going to be half ap times t square. Simply we can say, since the final velocity is equal to 0, we can use this formula, and this is going to be, after substituting this value of ap and the time till the rolling begin, after substituting all those values, you will be getting u square by 6 mu g. So that would be the displacement of point P in backward direction, you can say. So this is the uh, case over here. So work done by friction, or this would be the displacement in forward direction, since initial velocity is u and final velocity is 0. So this is the displacement in forward direction. Okay, and in work done by friction, simply we can say, so the displacement of this point P is in forward direction. So work done by friction, since friction is acting in backward direction, work done by friction would be negative in this case, and that would be magnitude of friction is minus mu mg into this displacement, that is u square by 6 mu g over here. So this will turn out to be minus 1 by 6 mu square over here. This is the work done by friction. So this we can say that is method number 1. Okay, so what we have done, okay, we have found out the displacement of point of application, okay, of the friction, and we have used the work done by friction formula, that is force dot displacement, in order to find out the work done by friction. The another method we can use alternatively is work energy theorem. That is, let's say, work energy theorem. So work done by friction would be simply equal to change in potential energy plus change in kinetic energy. So the center of mass level is not changing, so change in potential energy is definitely going to be zero. So change in kinetic energy only will be basically work done by friction. So before change in kinetic energy, we could find out like initial kinetic energy here is simply only of translational form, so that is half mu square, and the final kinetic energy would be in combined translational and rotational motion and rolling. Okay, so the formula which would be using is half mv square into 1 plus k square by r square, so that will give us 1 by 2 into 1 plus k square by r square will be 3 by 2 into mv square, and v was nothing but 2u by 3. Okay, so 2u by 3 whole square. So this is the final kinetic energy, and this turn out to be equal to 1 by 3 mu square. So obviously the delta k would be kf minus ki, which is equal to minus 1 by 6 mu square. So this is the another way you can find out the work done by friction over here. So we have done sufficient number of problems for rolling, and let's now discuss one another important concept, okay, which in the recent times JE has been have been asking, okay, and that is multiple axis rotation. Please try to listen very carefully. Multiple axis rotation. Sorry. Multiple axis rotation. Okay, so we will be taking the example of uh, precession of cone. Okay, let's take this example. Let's say we have a cone here, a right cone, let's say, of apex half angle. Let's say this is alpha. Okay, and its axis is, let's say, at this instant horizontal. For example, this is rolling on some this kind of inclined plane. Okay, and the axis about this axis, okay, it is undergoing rolling, okay, about, let's say, some angular velocity omega. Okay, so you must understand like this point here, which is in contact with the ground, okay, will be undergoing, say, a circular motion having this as center. So let's say this is the vertical axis. Let's define the axis as well. Say this is x-axis, this is y-axis. Okay, so as this cone rolls, okay, it will be at the same time it will be performing rotation about y-axis also. You must realize it will be performing rotation about y-axis also. So it will be having some angular velocity along y-axis, which is nothing but omega dash. So I hope you understand this situation. So this is a case of rotation at multiple axes. This cone is rotating along x or along the radial direction as well as along y-axis. It is rotating at the same time. Okay, so we are interested, so omega dash we don't know. Okay, omega dash we can find out using the value of omega. The only thing that is given to us here is this, the motion of this cone here is a pure rolling motion. That means there is no slipping at this point of contact. So using that relationship, firstly we would like to find out the relationship between omega dash and omega. So can we do that now over here? So only information we are going to use is there is no slipping at the point of contact. So now you imagine, okay, so we have to find out the relationship between omega and omega dash. Let's write it over here. Relation between omega and omega dash in relation in magnitude. So now you see this point, like when this cone completes one rolling about this axis with angular velocity omega, the time it will take to complete one rotation is going to be equal to 2 pi by omega. Can we clearly say that? Like this point is at ground. The next time it will again come to the ground will be after 2 pi by omega. Okay, so this must be equal to, in that time, okay, so this point on the ground will be moving from somewhere here to here, let's say somewhere here to here, and this length, let's say this is h and this thing is r, so this length is going to be the circumference of this circle over here, so this thing is going to be equal to 2 pi r. So what would be the angular displacement of this point P? Let's say this is phi on this circle over here, on this circle. So this phi, so this you can say is basically 2 pi r. So L, so L by phi you can say. So phi would be to this relationship we know. No, no, phi is equal to L, that is 2 pi r over here, and the radius of this thing is nothing but h, so phi is nothing but 2 pi r by h. So the time period of this means it is undergoing this uh, it is undergoing this much angular displacement phi in this much time. So what we can say, the angular velocity about, if this is omega dash, so this is going to be phi by omega dash. So phi we have already got it as 2 pi r by h into omega dash. I hope you understand what I mean to say over here. Like in the time when in which it will complete the rotation, okay, this point will again touch the ground, but when it will again touch the ground, it will come here. Okay, so this will be the angular displacement about y axis, you can say this is phi, and if this is 2 pi r, okay, and this radius is h, so phi will be defined as 2 pi r by h. Okay, so the time it will take would be nothing but phi by omega dash. So this is the relationship. We have equated the time, okay, to complete this one rotation, or this point to move from here to here, that will be equal. So that will give us simply omega dash is equal to r by h times omega. And looking at the geometry of this triangle here, okay, r by h is nothing but tan alpha, so you can simply write omega dash will be equal to omega times tan alpha. Okay, so the very first thing we were required to find out was the relationship between the angular velocities about two different axes of rotation. So now you see also the direction we must see, as we have seen the direction of omega dash is along y axis, and the direction of omega at this instant would be in this direction here. This is the direction of omega. So when we are to find out the, let's say, let's use other color pen, resultant angular velocity of cone, and angular velocity is a vector quantity, so we must add them vectorially. So as we have seen at this instant, over here, we are having omega in this direction and omega dash in this direction, and the value of omega dash, this is the vectors, and its magnitude, you can say omega dash is equal to omega tan alpha, we have already got. So the resultant would be in this direction. So this is, say, omega net. Okay, so omega net, you must understand the magnitude of omega net will be equal to, the magnitude of omega net will be equal to omega square plus omega dash square under root over here. So this will be like omega dash is omega tan alpha, so you can say omega into 1 plus tan square alpha, and 1 plus tan square alpha is equal to sec square alpha, and root of it would be sec alpha. So this would be simply equal to omega by cos alpha. This is the magnitude. And direction wise, let's say this angle is beta, so you understand that tan beta would be nothing but omega dash by omega, which is equal to tan alpha. So you must realize beta is equal to alpha. Okay, another thing we are interested in finding out in this situation is the angular acceleration of cone. We have already understood like net angular velocity would be nothing but omega, simply omega plus omega dash, the vector sum of omega and omega dash. So angular, the net angular acceleration would be d omega net by dt over here, which would be d omega by dt plus d omega dash by dt. So now in the diagram you must see that the omega dash is along y-axis and its magnitude is equal to omega tan alpha. So for omega dash, neither the magnitude nor the direction is changing. So this quantity rate of change of omega dash is going to be equal to 0. This is going to be d omega, that this quantity is going to be equal to 0. So we are left up with only this quantity. So now looking at this quantity, you must have realized like the value, let me draw this diagram again. So the direction of omega was in this direction. Okay, and this was rotating about y-axis with an angular velocity uh, omega dash. Okay, so you must understand like the magnitude of omega is not changing, only its direction is changing. So d omega by dt would be simply here, that would be omega cross omega dash cross into omega. Okay, so this would be the magnitude, this would be the angular acceleration. And if we wish to find out the value of magnitude of d omega net by dt, you can see, so that clearly you can say this, the angle between them is 90 degree, and this is the direction of say omega dash. Okay, so here the direction of d omega net, or simply the direction of alpha, will come out to be outward at this instant, so that means tangential. So this would be the direction of alpha, and its magnitude is simply going to be equal to, its magnitude is simply going to be equal to omega dash omega, and that will be equal to omega square tan alpha. So we have uh, established the direction as well as the magnitude of angular acceleration. We can have one another simple case of multiple axis rotation, and mostly I would like you to try. Okay, but let me give you some hints in this case as well. Okay, so let's have another situation when this time, let's say, one slant face of the cone is along the horizontal. This is the shape of this cone over here. Okay, and this is again rolling. This thing is rolling. Okay, let's say this here is y-axis. So this is rolling. So this point will always be in contact with the ground. Let me draw the circle. It would be drawing on the ground. So this is rolling, you can say. So about this axis, it is rotating, say, with angular velocity omega. Okay. And so at the same time, it would be rotating about y-axis with some angular velocity omega dash as well. Okay. So this is again multiple axis rotation, and previously the angle between omega and omega dash was equal to 90 degree, but this time the angle between them is not equal to 90 degrees. So now let's say this question, it is given to us. This apex angle is equal to, apex half angle is equal to alpha. Okay, so and say this is r, and say the slant length is l. So again, the first thing here would be to establish a relationship between omega dash and omega. So how are we going to do this thing? So again, we will be like for one complete rotation. Okay, that means this point will again, after rotating completely, this will again touch the ground. So this will move from, let's say, this point to this point, and this on the ground will be the angular displacement, some phi over here. So in this case, again, we will be writing the same type of equation. So the time taken for one complete uh, circular motion about this axis over here would be nothing but 2 pi by omega, and this phi here would be nothing but this time this length is 2 pi r definitely, and this radius of this arc is l. So phi here would be equal to 2 pi r by L. So phi by omega dash would be the time taken by this point to move to this point. Okay, since it is rotating with an angular velocity omega dash. So rearranging that, we will be getting omega dash will be equal to r by L into omega over here. R by L into omega over here. So now you see, so R by L, this quantity here, R by L, looking in this right angle triangle, R by L seems to be nothing but equal to sine alpha. So omega dash is equal to omega sine alpha. Let me write it again. Omega dash will be equal to omega sine alpha. Okay. My pen seems to be malfunctioning anyways. Let's complete this lecture. So omega dash is equal to omega sine alpha, and another two things we need to find out: what would be the net angular velocity and what would be the angular acceleration of this sphere, this solid, this cylinder over here. So now you see, for angular, net angular velocity, for, let's use other page. So net angular or resultant angular velocity, we must vectorially add omega and omega dash. So you must understand, this was the direction of omega, that was making, say, alpha angle with the horizontal, and this was the vector omega dash here. Okay, that we have already seen. Okay, and the magnitude of omega dash was nothing but omega sine alpha, that we have already established. So in order to vectorially add, let's resolve it into components. So if we resolve omega into two components, mutually perpendicular components, this would be omega cos alpha, and this would be omega sine alpha. We have all resolved this. So now you must understand, like the component of angular velocity, this component will cancel with this. So the resultant angular velocity would be in this direction over here. So that is omega net, you can say, and its magnitude is nothing but omega cos alpha. Okay, so in order to find out the acceleration or angular acceleration over here, angular acceleration. So now you see, like angular acceleration here would be d omega net by dt over here. So this is omega net, okay, and its magnitude, that is equal to omega cos alpha, is not changing, but this vector over here is rotating with angular velocity omega dash about y axis. Okay, so this is the direction of omega dash. Okay, so in that case, d omega net by dt, we can write it as omega dash cross omega net over here. Okay, so that will be equal to the direction. You can see the direction here at this instant would be outward. That means you can say tangential. So this is the direction of alpha. The direction of alpha is tangential, and its magnitude, here you can say the angle between omega net and omega dash is 90 degrees. So this is going to be simply omega dash omega net. Okay, so omega dash was nothing but omega sine alpha, and omega net was nothing but omega cos alpha. So this will turn out to be simply uh, uh, let's say here we are writing the magnitude. Okay, direction we have already shown, so that would be equal to omega square sine alpha into cos alpha. Okay, so here we have reached the time limit as well, so I have decided to cover as many concepts as we could have, okay, in this 6 hours session. Okay, so this is the conclusion. So here we have concluded the rotational motion. Next week we will be looking at the fluids. We will be looking at the fluid statics as well as dynamics. Okay, so let's say goodbye to each other. So thank you.